This is the North Carolina Department of Transportation Erosion and Sediment Control Certification Program Training, Level 2, Module 5, which is covering best management practices for erosion, sediment, and turbidity control. The presenter is Rich McLaughlin, professor in the Crop and Soil Sciences Department at North Carolina State University. As you can see here, we are essentially going to review the toolbox of practices that we use on construction sites to prevent or reduce the amount of sediment that leaves the project. Now, every construction project will have a set of erosion sediment control plans, which details what practices need to go where on the site. These are indicated as symbols, and there will be a key to these symbols on the plans, as you see here. All NCDOT projects will have the same symbols. We will review the practices starting from the outside and working our way into the construction site, which also coincides with a timeline for when these practices are actually installed. First, the site entrance pad and perimeter or outer limits. A construction site entrance or exit pad is needed at the point where vehicles are entering or leaving the site onto public roads. The following video is a review of your options.
So we're looking at a construction entrance pad. Remember from class, the key features are they need to be at least 50 feet long, 12 feet wide,
This is a diagram outlining the construction site entrance pad basics that we just described. All the practices we review will have these color diagrams, which are also available online, as we'll discuss at the end. As mentioned in the video, pressure washing manually or in a system may be necessary to ensure no mud is tracked onto the road. On the perimeter of the project, we normally have an orange fence or flagging. This should be the first thing installed because it will keep the equipment operators on the project and out of jurisdictional areas such as wetlands. It also helps to keep the public off the project. Follow the contours, and either wood or metal posts are fine. These are typical installation specifications with posts 2 feet in the ground and 10 feet apart. Flagging is typically used to indicate jurisdictional areas which should not be disturbed without a permit. These can be widely spaced, but should be clearly indicating the location of the area. Next, we review other practices that are typically located around the perimeter of a project. Silt fence is one of the most common sediment control practices on a construction site. Its purpose is to pool runoff and release it slowly through the fabric. This allows much of the sediment to settle before the runoff is released. Note that silt fences do not filter runoff, but they pool it. These devices are intended to be used for relatively small areas of drainage. Silt fences are supported by 5-foot steel posts with 2 feet in the ground. Silt fence material should be 3 feet wide, and 1 foot should be buried in the soil, leaving 2 feet to be attached to the posts. Posts should be 6 feet apart, unless there's a wire fence backing, or hog wire we call it, in which case you can go 8 feet between posts. This diagram shows how the material should be buried in a trench 8 inches deep and 4 inches wide. So the 1 foot of material is inserted and the soil is then packed back on top of it. This should be compacted to keep the material in place. There are machines that will trench in the fabric and compact the soil on top of it, and then the fence posts will go in afterwards. As with all sediment control devices, once the sediment has accumulated to 1/2 the height of the fence, it's time to do some maintenance. Make sure there are no gaps between the fence sections, or there will be sediment escaping there. I'm showing here a gap, and that's a problem. Since silt fences are often on the edge of the project, a failure, as you see in the right side, could mean sediment in wetlands or streams, which could result in fines and work stoppages. Never place a silt fence in concentrated flow, as you see here. There is not a single correct part of this installation of this silt fence. Remember the saying, if the bottom is flapping, it ain't trapping. A properly functioning silt fence will accumulate water behind it and slowly release it after the heavy sediment has settled out. Silt fences are sometimes compromised by equipment, or in this case, materials delivery, so frequent inspections are always important. In large storm events, the silt fence may not be able to release water fast enough through the fabric, resulting in overtopping and scouring on the outside. Sediment generated there could also create problems. To avoid overtopping, a silt fence may have an outlet installed. This releases water faster than the fabric. It should be located at or near a low spot in the silt fence. The silt fence outlet is constructed of a 5-foot posts, which are also inserted 2 feet in the ground, spaced 3 feet apart, and driven 2 feet into the ground, as I just said. Hardware cloth is attached to the posts, and washed gravel is placed on the hardware cloth. The silt fence outlet should be made up of that 4-foot wide hardware cloth, folded in the middle so that 2 feet are flat on the ground and 2 feet go up the posts. The gravel is placed on this to at least a 1 foot depth. Be sure there is sufficient overlap of the gravel on the silt fence to prevent bypass flow. The following video shows how this works during a runoff event. Here you can see the flow from a slope drain, which we'll talk about later, was directed down into this silt fence outlet. Some sediment is evident at the bottom of the gravel, as you can see. With most sediment control practices, the color of the water does not change because the fine particles are not retained behind these devices. We'll talk about how to attack those fine particles later. Another option for a silt fence outlet is a coir or coconut wattle, usually 10 or 11 inches in diameter. An example of the wattle is showing on the lower right. These need to be secured by installing wood posts on both sides at an angle to press them down into the soil. The outer netting should also be stapled down so that water can't get underneath the wattle. There should be a foot of wattle, overlapping the silt fence on both sides to again prevent water from getting behind the wattle. These are several more diagrams showing the correct installation of the wattles in a silt fence. Up here in the upper right, you can see those are staples that are through the netting, and they help pull that wattle down to the ground and keep water from getting underneath it. Notice the angle of the stakes as well. Those also help to push the wattle to the ground. Controlling where water flows on a construction project is important to be sure that the runoff passes through a treatment, like silt fence or a sediment basin, before it leaves the site. Diversions are used to achieve this goal and are usually placed temporarily during grading as the slope changes. This is a cutaway diagram of a typical diversion, although the dimensions are usually determined by the equipment operator. There should be grass established on these in order to prevent erosion on these diversions. Another option to getting runoff where you want it is a berm. The example on the left is showing how it is keeping the water from going down the slope, and the same on the right. In both these cases, we are diverting the water from the graded area into slope drains that keeps the water off the slope. So this is a cutaway of a berm, and again, notice the grass on it. And we need to establish that grass within 7 to 14 days after within 7 days after you establish that berm. One of the most important ways to protect slopes is to keep runoff from areas above them from running onto the slope. During construction, this can be achieved using temporary slope drains, as you can see here. These are usually 12-inch single-walled corrugated plastic pipe. This system requires that there's a berm at the top, as we just discussed, which collects the runoff and directs it into the pipe, which then carries it safely down the slope and into the ditch below so that the water is not going across the slope. This is a bird's eye view illustrating the number of important features of slope drains and diversions. First, notice the berm that extends into the roadbed. So the flow is coming this way. What that does is it prevents the water from bypassing this outlet, this slope drain, therefore keeping it from going down the slope and maybe overwhelming another slope drain. Another feature is a sump or a hole that's been dug. This pools the water and helps to drop out the heavy sediment before the water gets into the slope drain. This insert A shows another option, which is the most common inlet protection system, consisting of a ring of rock with a cover of gravel. This also pools the water briefly to drop out the heavy sediment. We don't want this slope drain to get filled with sediment. This is another view which shows that earth berm, preventing the flow from bypassing. It also shows the rock lining at the bottom to prevent scour when the water is released from the pipe. Speaking of scour, here's a couple of examples of what happens if you don't place stone at the bottom when you release that water from a slope drain. The special sediment control fence can be thought of as a silt fence on steroids. It's often deployed where flows are too much for silt fence, but other devices cannot be installed. As we discussed earlier, it can also be used as an outlet for a silt fence, as you see on the right here. The construction of this device is simple but effective. T-posts are installed 3 feet apart. Hardware cloth is attached to them. A 24 gauged galvanized metal material with 1/4 inch openings is what we're referring to with the hardware cloth. It should be that 4-foot roll we talked about earlier with the outlet, folded in half so there's 2 feet on the ground, 2 feet going up the posts, and you put washed 57 gravel on the hardware cloth to a depth of at least 1 foot. An alternative to the sediment control fence is a coir wattle. Again, for small drainage areas where you can establish these and have a little bit of water but get some control. As shown in the diagram, they need to be staked in and placed with at least a 1 foot overlap, as you can see here, to prevent water from getting around them. Again, they also have to be stapled in to make sure, as we saw from the diagram before, to make sure water cannot get underneath them. That's how these devices will fail, is if water gets underneath them. And here's an example at the toe of a slope where the coir wattles have been installed. Well, we've reviewed different ways to use ditches to direct water where we need it to go. We also have ways to prevent the ditch itself from eroding and adding sediment to the already heavy load in the runoff. These are called check dams, and the check means the flow is checked or slowed to keep it from picking up too much velocity and sediment. Here's a review of each of these. The first one is a wattle, which we talked about. Currently, the most commonly used ones are the coir or coconut fiber wattles or the Excelsior wattles. But wattles can be made up of tire chips and compost and all kinds of things. The diagram shows that the wattle needs to have a low point or a weir in the middle and then extended the wattle up the sides. This forces the water into the middle of the channel and keeps water from getting around it. As with the wattle barrier we talked about earlier, you need to have staples going through the netting. So make sure there's no gaps between the wattle and the ground, or water will cause a scour there. On the right, you can see we talk a little bit about adding flocculants, which we'll get into later. But these are chemicals that work on that fine material that we talked about earlier that cause the color. So here we have a bird's eye view showing we have a 6-foot blanket below the wattle. As you can see here, 6 feet of blanket. And that is going to help to prevent scour when the water goes over that wattle. We also can introduce the chemical here, as you see on the right, where we add 2 ounces of the flocculant on the wattle itself, and then we add 1 ounce on each side. So that on the blanket, here and here, and then of course on the low point of the wattle. Again, this is another shot of how that wattle needs to be installed so that there's a low point and the wattle extends far enough up so that we don't have water getting around it. And then we already talked about the flocculant, which we'll get into more detail in a minute. So this picture shows the correct placement of the flocculant. You see how there's a powder here. This is the flocculant, and this is about 4 ounces. So we've put 2 ounces on the wattle right there, and then we got 1 ounce on each side of the blanket. This way, when there's low flow and the water is going through the wattle, it will pick up some of that chemical and treat that turbidity. If we have high flow, then it gets treatment both from the blanket and as it passes over the top. It picks up some of that chemical. There are other forms of flocculant materials besides the granular form we've discussed. There are solid blocks, as you see here. There are socks that contain flocculant. There's rapid dissolving tablets, or fizzy tabs we call them. And then of course we've got our granular material, which is what we generally use. All of these should be placed in high flow water with lots of turbulence so the chemical can contact as much of the sediment as possible. This is an illustration of how flocculants act like glue and cause the smaller particles to stick together, and then they settle much like larger particles. So this is an example of flocculation. So these 3 columns of water have either been treated with what I'm calling an ineffective polyacrylamide, or PAM, one that has no treatment, and then one that is actually effective. You can see after 5 minutes, on the right-hand side, the effective polyacrylamide has cleared up the water quite a bit, while the ineffective polyacrylamide has done nothing compared to the one that had no treatment. And this illustrates the fact that we need to have some testing of the polyacrylamide you're going to use on your project to be sure that it will react with the sediment that's on the project. And there you have it. Very clear water with that effective polyacrylamide or flocculant treatment. So we also have some heavy-duty check dams that are used sometimes, which is the Class B stone, etc. We'll talk about those in a minute. But when you have these big stone devices, you can also use polyacrylamide. However, you don't put it right on the rock. You're going to need to put a blanket down. In this case, that's coir. And that's where the polyacrylamide granules are going to stick. You see, looking down here at our system we just talked about with the wattles and the blankets, there's lots of fabric, lots of places for the little granules to stick. With the rock, not so much, but if we add a blanket to it, and it could be Excelsior as well, then that's a great place for those little granules to stick. And when they stick there, they will start to dissolve during each storm event. All right, here we have a video in which we're going to talk about or demonstrate how this system works at our control site. So we simulate the construction site runoff by adding soil to water and then sending it into the ditch. On a real construction site, the flow would normally go into a sediment basin. And this will show you the beginning and the end. So you can see that that's a very effective treatment. Here's an example of what polyacrylamide looks like after the granules have dissolved and they're sticking on the wattle. So you can see where the arrows are. That's where the granules were put, and they kind of turn into a jelly that that dissolves slowly as the water runs over that wattle. Now this picture shows the flocculant on the wattle, right? However, they did not put any flocculant on the blanket. So as a result, the water that's going through that wattle is getting no treatment. And so you can see as it goes through, the color doesn't change. Furthermore, in this picture, you can see the flocculant has been covered up with sediment. So if you're looking at this wattle, you would want to replace the wattle and put some more polyacrylamide out, because this is not going to be very effective. All right, so let's talk about our heavy-duty check dam, the Type A rock silt check, which consists of the Class B stone. Those are those big rocks here, which was then covered up with washed 57 gravel. The larger rocks serve as a structure holding it in place during high flows, and the gravel serves to slow the flow down so that we get that braking mechanism that we want with a check dam. Note that some call the gravel a filter stone, but it does not actually filter anything. It just slows the flow. So here's some diagrams of the Type A rock silt check with some dimensions shown. It's very important that there's a low point in the middle. It's probably the most common error in these installations. Otherwise, flow can go around the sides and you don't get really much of a check dam effect. As we mentioned earlier when we were talking about the flocculant treatments, a rock check dam, if it's needed, can be used also as a flocculant treatment system by covering it up with a blanket. And here you can see this is the Excelsior used here. The flocculant is then applied to this blanket, and as the water passes through it, it picks up some of the chemical, which causes it to settle the fine materials. Here's a illustration of that. It's essentially the same illustration we had before, only now we've got a blanket on it. You can see what they've done is they lay the blanket on top of the gravel, and put a rock on each side. There's nothing to staple into, so you just need to put a weight on the blanket to hold it in place. All right, so here's an example. Here we have polyacrylamide placed on the blanket. So you can see it right here, but there's a little bit of a problem here. There it is, but there's nothing down here. So if we have water flowing through this ditch and doesn't overtop, then it's not going to get any treatment. So we need to get some treatment all through this area where water might be flowing. One thing while we're looking at this, note that this is a classic case of a check dam that was put in with a flat top. There's no low point in the middle. The Type B check dam is the same as A, but without the gravel layer. These will allow much faster flow through them, so they're only used in ditches with very low slopes and much less chance of erosion coming from the flow of the water. Here we have the cutaway view. Notice in this case, it's showing a tail, and check dams often should have a tail. This helps when the water is at high flow and overtopping. It sort of protects the downhill side when you have a tail like that. All right, so there's another practice that's used on the perimeter, going back to the outside here. It's called a clean water diversion. The idea is to divert runoff from undisturbed areas into a lined ditch and then sending it off the project before it can pick up sediment. This keeps the clean water clean and also keeps that runoff from having to be handled by the practices we are using for the construction site. In other words, you don't want a lot of clean water in your various practices inside the project. So divert it away, and you can divert it directly into the stream because it's clean water, doesn't have to go through a practice. And here's a diagram, pretty obvious, basically the same thing as all the other diversions, except we've lined it so that the clean water gets it onto the lined area and heads on down into a creek. And again, any areas that are excavated around where we're having water flowing, we want to make sure there is grass so that we're not seeing a lot of sediment moving into that ditch from that area right adjacent to the diversion. All right, well, at some point on most projects, a storm drain system gets installed. This means culverts under the roadway and pipes, etc. We don't want any of these to become clogged with mud. So there are a number of practices we're going to use to prevent that. So drop inlets will eventually be at ground level and drain roadway runoff through a grassed or lined drainage ditch. There are 3 types of inlet protection that we're going to use, depending on location and the expected runoff volume. Type A is the sturdiest of the 3, as it has the Class B or large stone covered with the 57 washed gravel. This will be located far from active traffic and generally receives runoff from a large area. Type B is intermediate with the Class A or smaller stone, and it will take runoff from a smaller area. Then finally, Type C is basically a silt fence outlet with hardware cloth covered in 57 stone or gravel, and this is from areas that are even smaller. This is a diagram of Type A inlet protection showing the general dimensions. Note that all 3 keep the stone about 1.5 feet from the inlet, mostly to keep the stone out of that inlet. The dimensions of Type B inlet protection are just slightly smaller than for Type A. Type C has steel fence posts on 4-foot spacings, and they either surround the inlet, as you see up in the top here, if water's coming in from all directions, or they may be placed on just one side of the inlet if the water is coming from just one direction, such as in a ditch line. As I mentioned, culverts also have to be protected when they've been installed. So if we're looking at very large culverts, we may be using a Type A for larger drainage areas, and then Type B for smaller areas. And the difference is just the size of the stone. So the Type A uses the Class B stone. So the large stone covered up with the face of 1 foot of gravel, always that washed 57 gravel. And again, that is set up with an area for settling the sediment so that it doesn't get into the pipe. And then the Type B uses the Class A stone, smaller stone, also with 1 foot of gravel on it, and also a settling area outside of this ring around the culvert. If your project involves roadway storm drains, these will also need to be protected if there is still bare soil on the project. There are many types. Some are inserted under the grate, as you see here. Others impound flow on the on the roadway, as you see here. They also require inspection and maintenance. So especially the ones that go inside the drain are prone to fill up with sediment. So you need to keep track of those before they actually will burst and release all that sediment into the pipes. You also have to make sure everything's still installed as well. So remember that all runoff on a construction site needs to pass through some treatment to remove the sediment. This generally involves pooling the water in order to drop out the larger particles or heavier sediment. But as you can see, there are many ways to achieve that goal. We're going to start with the smallest and easiest and move to the biggest. So the type B silt basin is sort of a leftover or holdover from the old sediment traps we used to be used as a standard practice. They're not very effective at trapping sediment, actually. They're typically used for short-term needs on small projects such as paving gravel roads. The outlet is the large Class B stone covered with the 57 or 5 washed gravel. These are typically installed in line with a ditch, and so they're essentially a ditch device. All of these traps should be a 2-to-1 length to width in size. This is the one case where you can have a steeper slope than 2-to-1. Again, because this is a measure that's going to be in for a short period of time. All right, well, the skimmer basin is really the workhorse standard sediment trapping device on construction sites. The skimmer, which you see here, is a surface outlet that rises as flow comes in and then slowly drains the basin down once runoff has stopped. When combined with porous baffles, which we see here, the skimmer basin can trap more than 90% of the incoming sediment. This is a great improvement over the rock dam sediment traps that only captured 50% or less. Looking at the bird's eye view at the top, we can review the key features of a skimmer basin. The diversion ditch on the left brings the water to the basin. It's usually put into a corrugated pipe, the 12-inch corrugated pipe, or a lined spillway right there. That way the flow doesn't cause erosion on the basin wall. We want the runoff to come into the basin from as far as possible from the outlet so that we will promote settling. There are porous baffles, which we'll cover later, which are across the width of the basin. These are evenly spaced, as you can see. The skimmer is attached via a flexible hose so that it allows it to rise and fall. And the outlet then goes through the dam and onto a pad of some kind of geotextile to prevent scour back here. There's a Class B stone pad under the skimmer right there that prevents the skimmer from sticking onto the bottom. The geotextile on the dam, we'll go back to that. So this is all covered with geotextile, can be stapled with any number of these staples. I think most of them are going to be using the typical staple as you see on the right. So when flow into the basin exceeds what the skimmer can handle, which is most of the time, the flow exits the basin through an emergency spillway, a term that's sort of a holdover from dam design. Temporary skimmer basins on the right will have the width of the spillway indicated on the plan. So this is the spillway. If it's a permanent stormwater basin, then the riser barrel will be where the emergency spillway is. Some of the specifics of the installation of the geotextile are provided here. again, the width of this weir is going to be on your plan. So every dam is going to have a different size weir depending on how much drainage area is coming into that basin. There are many different skimmers on the market, such as the Faircloth skimmer as you see here. We are wanting the skimmer basin to discharge fully over the next 48 to 72 hours after runoff ceases. So some skimmers have ways to restrict the discharge rate, as you'll see right here. In this case, the skimmer has an opening that's this size of the pipe, but that can be restricted by putting in a plug, as you see here, that has a hole put in it that's sized to allow for that 48 to 72 hour discharge after runoff ceases. So these are the approved skimmers as of now. The Faircloth skimmer, which we just saw, is very identifiable because it has a snorkel and usually has a color-coded tape around the snorkel that tells you what size the barrel is. They can be anywhere from 1.5 to 8 inches. Another skimmer is the IAS skimmer. It has a different design in which there's a single arm at the end with holes underneath it that allows the water to escape. The erosion supply skimmer, as you see here, is also a common skimmer. Looks a little bit like the Faircloth, but it has 4 legs, usually 2 or more inlets with trash guards, as you can see here. And it also has plugs that allow it to be used on different basins with different flow rates. The ProDrain 70, as you see here, has a unique way of adjusting flow out of it. The outlet pipe has a series of slits cut in it, as you can see here. And the sleeve on the outside is adjusted up and down to allow more or fewer of those slits to discharge. So like the other 2 we just looked at, this skimmer can be adjusted to have flows for different size basins. Now, notice here, the outlet for the skimmer has been installed in the dam at an elevation of about 1 foot above the bottom of the basin. Now, all skimmers will stop discharging once they are level. So at this point, we're not seeing any discharge. The standing pool that you end up with after that is actually a good system for allowing the dirtiest water after each event to stay in the basin and let it settle out some. And also it provides a break or a way of slowing the water that comes in on the first flush that comes into the basin. So there are several good reasons to keep a pool of water in the basin, as you can see here. Notice also there's a rope. All the skimmers should have a rope on them so that you can pull them over and maintain them. They may get clogged from trash or debris. The last skimmer we'll look at is the Marley float skimmer. It's actually having a redesign, so I don't have a picture of their newest version of this, but the old version anyway had a weight on it. These are weights that would push it down and water would come up underneath it and go out through the pipe. So like all practices, skimmers must be properly installed and maintained. The maintenance involves pulling the skimmer out periodically and clean it of trash, straw, or other floating debris that can clog it. That's why skimmers should always have that rope attached to them and staked to the side of the basin. So here's a few questions you should be able to answer regarding skimmers. Why do we have a standing pool? What is the weir for? Why is there a rope on the skimmer? So again, you should know the answers to all these questions. Here's an example of why we have to have a rope on a skimmer. So here's a Faircloth skimmer, and we looked at the discharge pipe and it was discharging nothing. There was no water coming out of that. And that's because the straw had washed into the basin and completely clogged that skimmer. So the alternative to having a rope on it would be you getting some waders on and going out and grabbing that skimmer. So it's a good idea to make sure that rope is there. When the terrain is very steep, installing a large basin would create a very high bank at the uphill side. So instead, we install a series of basins that are connected to each other. Runoff enters the upper basin, as you see here, often through a pipe or a low spot, and then the water goes through that, through the fabric, through the baffles, as you see here, and then it crosses over into the lower chamber, and sometimes there's 3 or 4 of these chambers, and again the water passes either through a pipe or across the dam. There may be a low point here in the dam, and we see another baffle and then a skimmer here. Now this actually creates a great situation for treating this water for turbulence, or sorry, turbidity. So here we go with this dam. We can either put if this is a low point, a weir, we can put flocculant, polyacrylamide, or similar materials here, or we could put them in the pipes. And so as the water moves from the upper chamber to the lower chamber, it gets treatment for that turbidity. The specifications for the tiered basin are shown in this diagram, but are essentially the same for a skimmer basin, just with a dam in the middle. In this example, the dam has a geotextile lined weir, as you can see right there, that low point, and that's used instead of the pipes through the dam. So it's one or the other. And again, here we have the corrugated pipe bringing the water safely down here without having any scour, and then we have the outlet is the skimmer. And again, pick your staples, but make sure that that geotextile on the dam is secured. Another type of basin is the infiltration basin. In some areas of our state, the sandy soils can actually infiltrate water so quickly that an outlet is not needed. Here you can see the porous baffles, but there's no skimmer at the end, just a dam with a weir in it. So the idea is the water will come in and then exfiltrate or infiltrate through the sandy soil and never have to pass through that dam. So here's a diagram of that. Pretty much everything the same except no skimmer going through the dam. Notice we have, in case of high flows, and this actually does overtop, going to always have to put some matting on the downhill side so we don't get scour. This is a coconut or coir fiber matting. And here's a cutaway view. Again, we've got the baffles, and we're going to fill that basin up if it does overtop here through the weir, but most of the water should be going out through the soil. Now basins sometimes are the old type with the rock and the stone as an outlet. And here's the front and cutaway views. You can see some of the details where we have the large rock, a weir cut in it, and then the face of 57 stone washed gravel, at least a foot thick. So what does that do? You should know by now it slows the flow through the rock and pools the water. So the type B dam is similar, just used on smaller areas. So it uses a smaller rock structure, but basically the same thing where we've got a face of 57 stone to slow the water and drop out the sediment as much as possible. Again, here's our cutaway of the type B dam. All right, so we're finally going to get to those porous baffles. The purpose is to spread the flow across the whole basin, which will slow the water down. They also reduce turbulence or flow up and down and sideways. Both effects help settle sediment much better than an open basin. We'll discuss their installation on the next slide, but let's linger here because this skimmer basin has everything you need to remember about their installation. On the left, you see the 12-inch corrugated pipe bringing in the water safely onto a rock pad. You'll notice the baffles are installed nicely, and we'll talk about the details, but they're nice and level. And then you get to the other end, you've got the skimmer with the rope on it, rock pad underneath it, and the lined dam. So try to remember these pictures if you want to think about how a skimmer basin works and what it should look like. This is exactly what it should look like. So porous baffles are made up of a 700 gram per square meter coir blanket. And just a side note, most of the world is on metric. So when we import something, it's going to be metric sized often. So it comes in a 2 meter wide roll that comes out to about 6.5 feet for us. The fence posts are installed across the basin with at least 3 feet above ground. So just like the silt fence, we've got 2 feet in and 3 feet above ground. A wire is run across those posts, and the fabric is then folded over that wire. We want to have about 3 feet of fabric as our baffle material. So remember, the fabric comes in a 6.5 foot roll. So if you have 3 feet on each side, then you have a little bit extra on both sides that you can staple into the bottom so that water doesn't get underneath that baffle. It's important that the sides are level so that water does not get around them again. In this case, you see a post used that you attach the material to. Other people will just run that wire across to a post in the or a stake in the side and put the material on that. Here's a case where they were trying to install the baffles as we just discussed, but they ran into rocks, so they could not put the post 2 feet in the ground. So they used a little ingenuity and supported those posts with 2 other posts on each side. So sometimes you have to improvise. To show how porous baffles work, let's look at a laboratory demonstration of an open basin. And the dye you see here is sort of representing your turbid, muddy water. So picture that. And here we go. You can see the flow coming in, a lot of turbulence. I've sped it up so you can see the whole basin has a lot of turbulence. So that's important to think about when we go to the next slide. And we look at what happens when you put a single baffle into that basin. All right. Now you can see the turbulence again, but watch what happens when we get to that single porous baffle. And we're going to see what happens to our muddy water represented by the green dye. So watch as it goes through the baffle. You see how there's no turbulence. In fact, as it seeps through, there's so little turbulence, it sinks to the bottom because it has the dye in it, so it's a little bit heavier. I'm going to skip forward so you can kind of see that. So this is why we like to add the porous baffles, because it really helps to settle the sediment much better than an open basin. All right, so another type of basin we occasionally use is essentially a dammed up ditch, the earthen dam with skimmer. So we use a skimmer as well as the baffles. The only thing different is we don't have a dam, a bank at the other end. We're just using the ditch as a settling basin. Do you see anything wrong with these baffles? Hopefully everybody noticed that the sides are slanted down. They should never be slanted down. They got to be flat or slanted up, one or the other, because we don't want water going around. So as you can see in this diagram, everything is essentially the same as the skimmer basin, except we just don't have the other end of the basin. It's all just in a ditch line. Lastly, there is the option of using a stormwater basin as a sediment basin during construction. So this would be the case where we had a stormwater basin that would have been installed anyway. So why not use it as a sediment basin or convert it to a skimmer basin? In this picture, you can see the skimmer attached to the riser and the baffles going up the sides. So a well-constructed skimmer basin that will eventually be converted into a stormwater basin. So here's a bird's eye view of a stormwater basin that's being used for sediment control. Again, we've got the baffles across the whole thing. Then we've got the skimmer installed with a riser. In this case, this is going to have an emergency spillway over here. That's a typical dam construction, as opposed to the temporary measures that we talked about, the skimmer basin, which would have a lower point right there as our emergency spillway. And more views, bird's eye, cutaway. So essentially the only thing that we're doing different here is instead of having a temporary dam, we're having a permanent dam installed, putting in an outlet, which will be used later, and using that outlet temporarily with a skimmer on it. All right, in this last section, we'll review what practices are used when working in streams or other bodies of water. Remember that permits are always needed. Special permits are always required when working in wetlands or other bodies of water. All right, so let's picture that your roadway is going to need to cross a stream. So your roadway is going this way. So you need to build a culvert in the stream for the road to get over it. In most cases, you'll need to get the stream flow out of your way to do that work. Here are some ways to do that. In this case, earthen dams right there are built above and below your work area. At this point, we've got a pump that's going to pump the flow from the stream around the work site. We're going to safely dissipate the energy with a rock outlet and get the flow back into the stream. So note that we're taking clean water and we're putting it back into the stream as clean water. So it never contacts our construction site. The other thing we might have to do is pump water out of the construction area. Often it seeps in underneath the dam or just from groundwater. But this is going to be water that's part of our construction site, so it has to go through a treatment system. So here we've got a pump. It's going to pump the water out, and we're going to put it through a dewatering device. And we'll talk about what those might be in just a few minutes. So here's a case where the project is underway. We're going to pump water around. Okay, another option would be instead to install a pipe in the dam and actually run the flow of the stream through the work area and just work around that pipe. A third third option would be to take that pipe and move it to the side and put the flow into the pipe. Again, we're damming up both sides of the project area and going to move the flow through the pipe and around the project. Finally, another option, the fourth option, is to dig a ditch and just divert the flow into the ditch. So that's probably the most common. Now this ditch would have to be lined because we need to make sure that this water, as clean as it is, doesn't get dirty from our construction. So it's going to go into just like a clean water diversion. Put it into a plastic lined or geotextile lined ditch and back into the stream. There are times when you have to work on the other side of a stream, such as installing bridge supports. In this case, you may have to put in a temporary crossing and remove it after the work is done. Geotextile is laid down, then a pipe is put in to allow the flow to go through, and then the riprap. This is the Class B stone, the larger of the stone, and then you top it off with the 57 gravel as your surface. The good thing about this is when you're done, you can pull all these materials out, the pipe and the geotextile, and the stream bed will essentially be undisturbed relative to what you might have had to do otherwise. So bird's eye view and cross section, again, got the pipe, we have the large rock and the 57 stone on the surface. Note here we've got the filtration geotextile underneath the rock, just like we talked about with the rock entrance. You have to put geotextile underneath rock or it'll just get pushed into the sediment or the soil. There's other types of devices you can use, such as pilings, or as you see here, or sandbags, or other types of things to separate the water from the work area. And these are also possibilities. Instead of using that earth dam above and below your project, you could use pilings or sandbags, or take a bunch of stone and put some plastic over it, etc. Lots of different options for damming up those streams. So we just discussed earlier how pumped water from a construction site always needs to go through a settling device before it's released off the project. One of the treatment systems is a stilling basin, which you see here, which has porous baffles, again, and a stone outlet. So as with the skimmer basin, the flow should be brought into the basin without any erosion and as far away from the outlet as possible. So note that the rock in this outlet is going to be specified by the design engineer. Also, we have an over excavation, so you see there's going to be about a foot of water that's going to stay in here when there's no pumping. And at the end of the pump line, at the hose end, we've got a pile of rocks to prevent scour. Lots of little features that are important to keep us from discharging a lot of sediment. The other option for discharging pump water is what's referred to as a special stilling basin or a sediment bag. This is a geotextile bag sized according to the expected pump flow and sediment load. These are often used when space is limited and you can't put in a stilling basin. The bag needs to be placed on a level area on washed gravel, you see on the left, or on pallets, and these allow flow out through the bottom of the bag as well as from the sides and the top. It's critical that the area is level, otherwise the bag may start rolling if it gets too full. Also, make a plan for how you're going to remove that bag. Place straps underneath it or some kind of a netting, something that will allow you to lift that bag, because if you try to pick it up with an excavator or something like that, it's probably going to tear and all the mud will just come spilling out. So this diagram shows other key elements of the special stilling basin, including that filtration geotextile underneath the stone to make sure the stone doesn't get pushed down into the dirt. All right, well, you know, there are many resources available to help those responsible for erosion and sediment control on an NCDOT project. These include several manuals. These are all online, a handy flip book, a field guide, and of course, the actual erosion and sediment control plans themselves. The erosion control erosion sediment control manual is all online, and all the pictures that you've seen should look familiar. They're right out of this section. Lots of good information about where these practices need to go, practices that you need to follow, as well as problems that may come up. So these can be located here at this website, connect.ncdot.gov, and you can look here down to the soil and water for design guidelines, and over here there's the manual. So you can download the whole thing, and you'll have everything on your computer ready to go. If you want to see standard drawings, some of which we've seen here, you go to Division 16 in this website. As you can see, Division 16, and it'll give you lots of drawings if you're interested in looking at those. And there you go, standard specs. So remember, the 3 principles for all of our best management practices: they're installed correctly, inspected often, and maintained as needed. This is the end of Module 5 for Level 2 BMPs.